Okay, good evening. So the idea today is to give a high-level overview of machine learning and especially supervised learning, introduce the main ideas and show you some examples on how these models and these ideas can be very easily implemented using a library called sci-kit learn. So the language I will be using when showing some example is Python. The main reason is that if you want to apply machine learning and, for example, as a data scientist, you will always end up encountering Python. This for several reasons. Because it's flexible, you can use it as a scripting language, as an object-oriented language, and it offers also tools from functional programming. But mainly because it's very fast for prototyping. So if you want to just code your model away and try it out and see how it goes, it's always the first choice to go. Then you might want to improve it for performance, and you may choose another language, but for prototyping is usually the best choice. Especially because the Python can count on a huge open source community that develops many different libraries that take care of pretty much all the most boring parts of data analysis. So there you have NumPy, which implements fast matrix operations at a very low level using C and wrapping very low-level libraries which perform really fast. You have Pandas for data loading and transformation, and LTK that takes care of natural language processing, and sci-kit learn, which offers a wide range of supervised and unsupervised learning models. There are also the most common libraries used for neural networks are also implemented or offer an interface to Python. So fundamental features of the language is just that it's an interpreted language with dynamic typing. This means that you can just change the type of the variables at runtime with with a high degree of freedom. And it offers a just-in-time compiler to speed it up. It's called PyPy, and it's compatible with most of the libraries in Python. And that can be useful if after prototyping you want to actually put the code in production. In general, Python is very understandable, so you should be able to understand the code even if you have some basic programming exposure, you should be able to understand some Python code. The only weird feature of it is that indentation is not optional. Indentation is part of the syntax. So code blocks are not surrounded by parentheses or brackets like in all other languages. You actually delimit code blocks using the indentation. You can use spaces or tabs, but just don't mix them because otherwise weird things happen. When I will show you some examples, I will show them using Jupyter, which is a notebook. It's a sort of web-based interactive scripting environment. You can download it very easily if you have Python installed in your computer. Just by typing, if you download Anaconda using the Python distribution Anaconda, you can just type conda install Jupyter and you'll have it on your computer, and you can run your scripts inside the notebook. All variables will be saved, and you can iterate over your experiments. So, as first thing, I would like to give you an introduction of what machine learning is. So, machine learning can be thought as a field of study, but also a collection of algorithms, ideas, and techniques that enable us to design systems that improve their performance on doing some specific task as they gain experience in performing it. And there are three main areas within machine learning, which are supervised, unsupervised, and reinforcement learning. These three main areas differ mainly upon the type of experience that the system is exposed to during learning. Supervised learning is the simplest form of machine learning, and the experience comes as a set of input and output pairs. So you are given a set of input and outputs, and the system must learn to predict the output given the input. So for example, you might be given a set of data concerning houses in London. So you'll have the size of the house, the area of where the house is located in London, the floor at which it's located in the building, or other features of the house. And then you might be given as output the price at which the house can be sold. The system should learn to map those features and learn a function from those features of the house to the price. Obviously, the important thing is not to be able to predict correctly on the data set you're given, but to generalize to new data. So if you're given a new house, which is also located in London, and shares some features with the houses you have been seen in the past, you should be able to give a reliable estimate of the price, even if you've not seen that specific house previously. So this is supervised learning because you're given a very strict supervision upon the system is given a very strict supervision. For every item he needs to try to predict, he is given the correct answer and he's informed about if his prediction was correct and wrong and given the chance to adapt. Another type of learning is unsupervised learning. In unsupervised learning, the system is just fed a stream of experience, which comes as some multidimensional data. And the aim is not to learn to predict correctly an output associated to this data, but rather the idea is to try to find structure in the data. So you might want, for example, to find clusters in data, you might want to find better representations of the data, or you might want to reduce the dimensionality of data. So for example, going back to our example with houses, you might have that some features are actually relevant to predict the price, or some features can be predicted from other features, and you might be able to compress your representation and save space just by observing the underlying structure of your data. The third type of learning, which is a major part of machine learning, is reinforcement learning. In reinforcement learning, the experience comes as a sequence of decisions. So your experience, this experience the system is exposed to, is a set of observations after each observation is asked to make a decision. And the decision affects the environment which he is embedded in. So the system, which is usually called an agent within reinforcement learning, must learn to make good decisions in order to maximize some reward signal which is provided by the environment. So in addition to observation, periodically he is fed the reward which gives him an indication of how well he is doing. So for example, if you try to teach by reinforcement learning a system to play a game, he might act at each turn. He is fed the state of the game and he is asked to take an action. And at the end of the game, he will be fed a positive reinforcement or a negative reinforcement, depending if he has won or lost the game. What you can see is that the problem is much more difficult than in supervised learning, because in supervised learning, for every choice you make, you're given the right answer immediately and you can adapt to it. While in reinforcement learning, you have a very delayed signal and you have played an entire game. Maybe some moves were good, some moves were terrible, and you won it, but which moves were good? Which moves were actually the reason you won? This is very difficult to somehow backtrack the information across time to understand how you can play better. So, machine learning is part of a broader field of artificial intelligence, which aims at try to build systems which can reproduce the human intelligence. This starts very early in the history of computer science. So in the 46, we had the first general purpose computers. And already in the 50, Turing started investigating and wrote some papers debating if we could use computers to reproduce human intelligence. His focus was on evaluation. So how can we even recognize if a system is actually intelligent? He had a very pragmatic view. So his view was if he is indistinguishable from humans on some task which is sufficiently complex and high level, we should somehow just recognize him as being intelligent. Nowadays, probably most people would not agree that it's just enough to be able, for example, the Turing test was to be able to sustain a conversation on an arbitrary topic in natural language with a person. This is certainly high level and very complex task, but most people nowadays would not agree that it's enough to deem a computer to be actually intelligent. In the 50s already, there were other first experiments on different sides of intelligence. So Samuel used games to investigate planning. Planning is one of the basic human capabilities, and it's very useful in games because you can plan ahead to try to win your game. He focused, I think, on checkers. And he was able, using some form of state space search, to build the first agents which could actually play checkers to a reasonable level. Simon, in the same years, focused on another side of intelligence, which is reasoning, especially logical reasoning. And his work was on developing automatic theorem provers. He believed that logical reasoning was actually the main fundamental feature of human intelligence, and if he could build a system that could, for example, prove theorem in mathematics and things like that, he could actually do something really important to actually achieve an artificial intelligence. He achieved a lot of success in automatic theorem proving, but he didn't actually make big progress towards artificial intelligence. I think one of the reasons is that besides reasoning, one of the features which is fundamental for actual intelligence is learning. So learning is the focus of machine learning, and started the first experiments go back to Rosenblatt again in the 50s, who developed the first model of the neuron, of the biological neuron, and which he called the perceptron. That was a very simple model, a very simplified model, but was interesting because he could adapt its weights and its internal mechanism in order to improve on some simple tasks, and was the first actual agent capable of doing this. These were kind of cool results for the 50s. They had just discovered the computer and already they could do some interesting stuff. But for a long time, actually, nothing else happened. Mostly because in the 60s and 70s, there had been a big hype around artificial intelligence and high expectations, which could not be fulfilled at the time. And the result was that funding was cut all across the machine learning community and artificial intelligence community. Both governments, industry, universities, everybody tended to step a bit back from a subject which had failed to deliver what they were expecting. It took until the 80s for some parts of artificial intelligence to come back into spotlight. So in the 80s, there was the development of the backpropagation algorithm, which could be used to train efficiently the first artificial neural networks. And these were used actually in some commercial application, very successful, mainly thanks to the use of convolutional neural networks by Yann LeCun. And in the 90s, we had another side of machine learning, which was more based of statistical and probabilistic modeling, which also had very big successes in different fields. And finally, in 2006, there were published quite a few papers by Benjo, Hinton, and a few other researchers, which showed that the artificial neural networks that had already been used in the 80s, for example, for image recognition, could actually be scaled to many different additional problems by relying on graphical processing units, which is a specialized type of hardware which was developed for a totally different reason, but which could be adapted to be used for machine learning and train much bigger models than it had ever been tried before. And this led to a huge success across a range of tasks and to the current state of the art in machine learning. So we have, for example, the main applications today go across machine vision and natural language processing, especially, but also you can find applications of machine learning in marketing, in finance, in game playing, in business intelligence, robotics, even health, and obviously web search and online advertisement. Basically, wherever you have huge amount of data, which you want to process and extract some insight from, machine learning becomes one of the few tools you can actually use to do that efficiently. So the main focus today will be on supervised learning, which is, as we said, that kind of learning in which the experience comes as a set of input and output pairs, and in which you want to learn to predict the output given the input. So your input is usually a multidimensional data. So your input may have different attributes. As we said, for the house example, you could have the size of the house, the area where it's located, you could have the floor at which it's situated, and many other features. And then you have one single output, which instead you want to predict from all these features. And as we said before, the fundamental property is that you do not want to learn that data set of mappings. You don't just want to store them in memory and being able to put them back out when you ask for it. You want to generalize some knowledge from those pairs of inputs and outputs that will then allow you, if you are provided new inputs that are generated by a similar phenomenon, problems, or setting, you would still be able to predict something meaningful from those inputs, even if you have never seen them before. So there are two main areas within supervised learning, which are classification and regression. They differ mainly on the type of output you are trying to predict. In classification, the label, y, the output you are trying to predict, assumes values in a finite discrete set. So you could have that you want to predict if the house is expensive or cheap, just a binary classification, or you could have multiple classes. You could have red, green, blue, true, false, but it must be a finite set of choices which you want to discriminate between which. While regression is a different type of learning, is a different type of supervised learning, in which the quantity you want to estimate is a continuous value. So it might be the price of the house in our previous example, which can assume any value from 0 to infinity, especially in London. And so we'll focus first on classification because it's maybe easier to understand the main concepts. And we will take as example a small but quite common dataset, the iris dataset. This is a dataset which contains 150 samples of flowers of the iris species, which are divided in 3 groups of 50 samples each, which are 3 different subspecies of iris. And they are, well, setosa, versicolor, and virginica, and they correspond to the 3 different colors on the plot. As you can see, this is a very simple example. There is some clear structure. You don't really need machine learning. You can just look at it and you see that there is that the different species cluster in different regions of this plane. This plane is each dot corresponds to a sample of our dataset, and the 2 axes are the petal length and the petal width of the flower. You can see that if, for example, your flower has a small petal length and a small petal width, it will be most likely a setosa iris, because the dataset is clustered already naturally in very neat and precise areas. So if, very intuitively, if I'm given a new data point which is here, I think most of you would agree that it's most likely blue. If you're given a data point in the middle, most of you would agree that it's most likely to be a green data point. The problem is that all our description or our intuitive reasoning, okay, if it's in the bottom left of the plane, then it's blue. It's obvious, but it's not something that a computer can easily process. You need to convert your reasoning in something that a computer can actually process and act upon. And not only, but you also need something that can learn on its own, because if it's a simple example with just 2 variables, you can easily see and fabricate some rule. If you have hundreds or thousands or tens of thousands of these variables, there's no way you can just plot it and hope to see some meaningful relation. So, for example, one way we could encode our reasoning about how to classify our iris samples is through what is called a decision tree. So a decision tree basically represents your classification process as a sequence of decisions. In our case, we have 150 examples, and we can first ask if the petal length is below a certain threshold, 245, because we can easily see that if the petal length is on the side of this, then it's certainly blue. If it's not the case, you can then try to analyze the subset of data which does not satisfy this condition and apply a new condition to further partition your data. And just by following your decision tree until the leaf, you arrive to predict what type of iris you believe it should be, with a very simple and straightforward structure. So this is nice because you can easily encode this in a data structure on a computer. But what you want is that what is important is that a structure like this you can actually learn from data alone, just by applying some simple rules recursively and just building top-down your tree. So basically what happens, I'll give you just an overview of the algorithm and then show you how it actually works using scikit-learn. The basic idea is that you start with all your data samples in one node, and then you consider one by one the attributes of each sample of this data set. So petal length and petal width. You consider first one and then the other. And for each of these attributes, you try splitting in different points your data set. So if this attribute is smaller than 2, smaller than 3, smaller than 5, you try different split points. And you select the splitting, which simply makes the data in the 2children node most homogeneous. So you would like, for example, the first is a good split because you get a children node where you have all data points of 1 and no data points of the other 2 classes. This is an excellent point. So you split on that. Then you consider a second point. You test both attributes. You try different splits. and you select the split that gives you most well-separated classes within the child nodes. So here you get 49 and 5, and there 145. It's very, very homogeneous nodes, and that is good because it means that you can then predict with a very good accuracy what it will be. And just by applying this procedure recursively, you can actually build something like this very fast and independently if you have 1, 2, or 1,000 features that your dataset is composed of. One caution is that if you just go on splitting, you might end up just having each node with one sample, and that means that you actually have learned anything. So what you have to do is actually to stop your process of splitting when your children are homogeneous enough, where what is this enough is a parameter that you have to set and you have to experiment with. So this is a very simple model, and it works well on a surprisingly big number of problems, but you might believe that you can come up with something better, and indeed many people have. But how do you measure if something is better? In what sense is a model better than another? The criterion in supervised learning is always how well it does in predicting new data that you have not seen before, how well you are on that kind of data. Not how good you are on the data you have been trained on, because that is easy somehow. There are two main ways of evaluating models. The first one is the simplest thing you can think of. You have your dataset, you divide it in two subsets, a training set and a test set. You train your models using exclusively the data points in one of these two sets, and then you try to predict the data points in the other set, of which you know the correct answer. You evaluate how accurate you are on those, where accuracy is just a fraction of data points you predict correctly. And this gives you a good estimate of how well your model has done. And you can try different models and evaluate them on the test set and see how good they do. This is obviously simple and maybe the most straightforward thing you could do, but there are some caveats, because, for example, you are wasting data. You are devoting an entire portion of your data to not be used for training. And this is a problem because in supervised learning, most often somebody has labeled your data, or finding or collecting this data with the input-output pairs well labeled, clean, and ready for analysis is very costly and expensive and possibly slow. So you don't really want to waste data. In my thesis, I was doing, for example, summarization with supervised learning. You would have that for every document I had to summarize, somebody had to create manually some summaries for it. So it was difficult to have even, 200 documents with a corresponding summary. So I could not afford to waste 50% of it just for evaluation. So a better method, or an alternative method, which is often used, is cross-validation. The idea behind cross-validation is that you take your full dataset and you divide it in k subparts, in this case, four parts. Then you run k experiments, in this case 4 experiments, in which you always test on one of these subsets and train on all the others. And you do this repeatedly, changing the subset you are training on. And then you take the mean error across these experiments as an estimate of the error you would get when you train on the entire dataset. So you get to use all your data for training, but you get an estimation not only of the error which is likely to have on new samples, but also on the uncertainty you have about on this estimate. So you might take your mean and you get that your model is 90% correct, but you can actually, analyzing the variability across the different experiments you have done, you can also get an interval of how confident you are. So you might be 95% confident that it's between 88% and 92% the actual performance of your model. So you get both a reliable estimate, you get to use all your data, and you get also a measure of how much you can be confident that your estimate is actually meaningful. So this is nice. So you have many models, you have ways of evaluating them, but one might think, for example, that some models are just bound to be better than others. So I should not even test if a simple model is good if I have this super powerful model which is much more flexible, much more powerful, and will always perform better. It turns out that this is not the case, and actually there is always a trade-off. So the more complex your model, the more data you need to train on. If you apply a very powerful and very complex model on a small subset of data, what's happened is that you will get a very little training error, a very low training error, but your test error will actually get bigger than what you would have got trying a less complex model. So it's you always need to go back to validate your experiments on a whole data set or by cross-validation. You cannot just choose the most powerful model there is and use it because he is the most powerful and he will work better. So one thing I wanted to do now is just show you how easy it is, for example, to classify and build a model with scikit-learn.
Do you want to show this?
Yeah.
And do you want them to follow along? Because there was a link for it.
Yeah, so there was a link
It's
which
on the first slide.
on the first slide and on the web, on the Facebook page.
Yeah, it's on the Facebook page as well.
There's a
link.
link.
It's uclutech.com/ml1, and that takes you to these notes. Literally, so everything he's kind of said is on these notes, so you can download the repo with the code.
And you can download also the notebook.
Sorry
I will
for
show you
interrupting.
some experiments with. You don't have to do it. You can just follow me if you want.
Yeah.
You can also download it after the workshop if you want to check things again. But if you want it, here is the link. You can download the notebook, but you will have to have installed both Python and Jupyter beforehand. So this is what a notebook on Jupyter looks like. You get an environment which has cells. You can run each cell independently, and what the variables you define and you initialize in these cells are available all across the entire notebook. So the first thing I will do is import some Python packages. This is done with a very simple syntax. You just do import name of the variable, and if you want, you can specify a short name for reference when you want to actually access that library in the code. And I will import NumPy, which is a library for fast matrix multiplication, and matplotlib, which is the main library to create plots, and scikit-learn, which is what I will use to actually train a decision tree. Importing from scikit-learn import, it's the alternative syntax to import not the entire package, but just a subset of package, just the part you actually need for your experiments to avoid loading the entire package, because scikit-learn is quite a vast piece of code. You can, importing from scikit-learn import dataset, this provides a lot of commonly used datasets for supervised learning. And in particular, it provides the example I talked about before, the iris dataset, which can be loaded with a very simple syntax, just datasets.loadiris. Here I'm just looping over the feature names of this dataset. You see that there are 4 features. The 2 we had considered before, petal length and petal width. Another 2 which we will not consider because they are less useful. And here I'm slicing the datasets. So iris.data contains the actual matrix of the attributes for each sample. And with this syntax, the column means all rows, and 2 to 4 means all rows, columns from 2 to 4, where 4 is excluded. So it's actually column 2 and column 3, which correspond to petal length and petal width. So you can see how you can just plot your data if you want to have a first want to observe your data. You can do it very easily. You just create your plot with plot figure. You specify the size of the plot. You can set the axis names and the title. And then with this simple syntax, which takes the first attribute, the list of first attributes, the list of second attributes, and the target, you get your plot of the entire iris dataset very cleanly in just 3 lines of code, which was also the one you saw on the slide. And then if you want to train a decision tree and evaluate it using cross-validation, also this can be done very easily with scikit-learn, because you just initialize a variable decision tree classifier, which is an object, which is a class which is provided by scikit-learn. And you can use the utility cross-validation, which also comes from scikit-learn, which takes one classifier of whatever type, your set of attributes, your set of labels, and the number of experiments you want to do during cross-validation. This very easily trains the model and provides you the results. So if I run using Shift-Enter, I get an error because I have not run since the beginning. Okay, so you get your scores here. You see that across the different experiments, you got different levels of accuracy. In one case, you actually did 100% of your accuracy in predicting. In another case, you were less good. Here is 90% and 96%. Overall, you get that your mean accuracy is 96%, but because you're computing the standard deviation of your variability across experiments, you actually know that you must not trust too much this 96%. It could be down to 89 or up to 100%. That's approximately the range you can actually expect it to perform if you give him new datasets, somewhere between 89 and 100. So all of this training, evaluating, was not even probably 15 lines of code. And this is why it's very useful to use scikit-learn, because it really provides you so many utilities, so many models to do whatever you actually need to do. So,
maybe a good idea to tell them how to use Jupyter. Definitely do
that. How many of you have actually installed Jupyter? Okay, cool. How many of you have downloaded the code? A bit less. Okay. So, if you want to try, as a first example, is try to do the exact same thing. In the code you have downloaded, there is the code that I just showed you, and then there is a second section where you can try to do the same experiment, but loading a different dataset. This is the digital dataset that contains the handwritten digits, downsampled to quite a low resolution to make everything simple and smooth. And you can basically just apply the 2-3 lines of code I showed you before. You load the dataset like this. You call cross-validation, passing him a decision tree, and he should basically return you the same results I showed you before. So I was thinking maybe I could give you 5 minutes just to try out Jupyter, manage to open the notebook and try out, and then I'll show you how you can do it. So if you have problems accessing the notebook and you haven't installed it, you can just type in your terminal, Jupyter Notebook. This will automatically run a web page, will open a web page, which now I will move on the right screen. So this.
I think this is full screen.
So this will open a web page in your browser like this, where you have your code. And if you have moved to your folder where you have downloaded your repository, you can just open your code by clicking 2 times on the Python notebook. Okay, I see that quite a few people are having some problems actually downloading the notebook, so maybe it's better if I walk you through the code, and you can then look at it on your own at home. So the way you could do, for example, the handwritten recognition problem is, again, you just import the packages you need, which in this case are the same as before. Loading the dataset just goes as by the previous example, so digits, you assign it to the variable digits, just datasets.load digits. You can then put your dataset into 2 matrices, a matrix of your data and a vector. This is how the data look like if you just loop over your dataset and plot the first 10 samples. And the training the model, again, in scikit-learn is very easy. You just pass it to your cross-validation utility, your model, which is a decision tree, your data, and the number of folds. This gives you an evaluation of how good your model can do on recognizing handwritten digits. And you see that given that the problem is less trivial than before, you get much lower accuracy. You go down to 78%. The data points look like this. They are very low resolution images just to make the data set smaller and more manageable. In the GitLab repository, you get both the version without this and the solution, so you can actually check out all the details at home. This is just to give you an idea of how simple it is to do things in scikit-learn. Okay, so this parameter here is the number of experiments you're making. In cross-validation, you divide your dataset into a certain number of subparts, and you always test on one and train on all the other, and you change which one you're doing in all experiments. This is the number of subsets you are considering. 5 is the usual number. Yeah, exactly. It's just how fine-grained you do your cross-validation. Obviously, the higher this number, the more accurate your estimate, but the slower it will be because you will have to train your model again and again. The most common thing is to do 5 or 10-fold, depending on mainly on how much time you want to spend training your model. 5 is a very common choice. These images are provided in the scikit-learn datasets already downsampled. They are already a simplified dataset. Okay. So, this was a very simple example. But you've seen that even on this simple example, so you have a dataset of digits which have been downsampled, so to make the problem easier. But even so, if you just apply a decision tree, you actually get not such a good performance. You get about 78% performance. So even go from a very, very simple example like Iris to a quite simple example like the data I showed you before already led us to a serious drop in performance. This is because the decision trees are fundamentally a very, very basic and simple algorithm. So I wanted to show you one simple way in which you can actually improve performance of your model even without using particularly complex ideas and models. This is ensembling. The idea is that you can actually boost the performance of your model, even of very simple models, by combining many of them. So, this is not nice. Okay. So, what you could do is to train many models of possibly different algorithms, totally different models, or of the same model, but introducing some other randomization, as I will show you later. And then combine their predictions. So each of them says, this image for me is 2, this image for me is 3. Each of them predicts what he believes the image is. And then you just do majority voting and you select the outcome which is most often predicted. This might be a very straightforward idea, but you can actually perform, you can even using such small, simple components like decision trees, if you put many of them together, maybe 100 of them, you can actually achieve very good performance. The way you do it usually, in the case of decision trees, is by using bootstrap aggregation or bagging. So this idea is that you take your dataset and you split it in many subsets, and you train a different model on a different decision tree on each of these subsets. So all your models, which you will then aggregate, are trained on different subsets of the data. And what is done usually with decision tree is that you don't only partition your dataset, but you also partition your features. So each model will be trained on a different subset of the data and using only some of the attributes of the inputs. And which attributes will be just chosen at random and different in every model. Then you pack together all these decision trees, train on different data, different features, different attributes, and you do majority voting. This is called the random forest, and it's one of the most popular methods, for example, on Kaggle. Kaggle is a website where companies put their data science and machine learning problems, and everybody can just compete and submit its model, and possibly earn also significant amounts of money. And very often, what actually turns out to win the competition is something like this, a decision tree. Possibly combining many decision trees, because you can do aggregation at all levels. But this is actually a very powerful way of dealing with the supervised learning problems. So if we see, if we try, for example, this simple idea on our simple data set of handwritten digits, we can see that we can actually improve performance hugely. So before we had went down to 78% accuracy. If you run the random forest using just 10 decision trees, so a very small number, or usually you use 100 or more, you actually already go up to 89%. So you have gained more than 10% in accuracy just by putting together 10 decision trees and doing majority voting. And majority voting is just aggregating the results. So each model makes its own classification. He takes an image and he predicts what number he believes is written in this image. And each model does this with the same image. And you just select as actual output of your model the most voted image. So maybe 5 of them believe it's a 1, but 1 of them believes it's a 7. Because they are quite similar, you can get confused. But given that 5 have voted consistently on 1, you will predict 1. So how I measure performance is using cross-validation. So it's what I explained before. So cross-validation is you take your entire dataset, you split it into k subsets, you test on one of these subsets your model, which has been trained on all other k-1. And then you run k experiments, changing the subset you use for testing. And then you take the mean of your accuracy, which is the fraction of correctly classified items in your test set. And the mean of these accuracy, you take it as estimate of your error overall. While the standard deviation of this quantity you use to measure the interval of uncertainty you have on the accuracy of the model. The second part of supervised learning is regression. Regression is when...
What's the optimal number of subsets for the cross-validation?
You use either 5 or 10. If you have a big data set, you will use 5 because it's you have to train as many models as the number of subsets that you have, so that might be expensive. And if you have a very big data set, then you will probably use holdout because you don't have problem with wasting data because you have a lot of data anyway, and that way you will train the model only once. So cross-validation is usually used when you have smaller amounts of data, so training repeatedly is not a problem, but getting a reliable estimate is very difficult. So you use cross-validation to improve the reliability of your estimate. So the second area of supervised learning is regression. Here, as we said, the labels are continuous values. You want to predict the price of the house, you want to predict the amount of rain, the milliliters of rain that will be next year, or some quantity which is not bounded to a discrete and finite set of categories. This is a completely different problem in a way. So most algorithms which are used will be significantly different because different is the fundamental aim that which you are trying to achieve. This is a dataset, advertisements versus sales. So you have on the x-axis, you have the amount you have spent on advertising on a specific device, so television, radio, or newspaper. And on the y-axis, you have the amount of sales that you have achieved. So these two, there is a trend, but not, here there is a trend, but not so clear. Here it looks like newspaper advertising is mostly useless. The stronger pattern seems to be on television. So if you actually spend more money on television advertisement, you seem to be getting actually bigger sales. So, but one would like maybe to quantify this information. How much more will I earn if I double the amount of money I spend? Because there is quite a variability, but if you want to get a good estimate, how could you do? This is a regression problem because you want, given the amount of money, predict how much I earn. So one thing you could do is linear regression. Linear regression is the simplest model in regression. You try to fit a line. You assume that there is some hidden relationship between how much you sell and how much you spend on television. And that this relationship is just some value times how much you spent on advertisement on television plus some constant shift. It's a very simple model, and the aim is to find which line best approximates your data. So for each of these data points, you have an error on your dataset. An error which is the difference between the true value of your sales and what you predict to be the value of the sales. What you want is that overall, across the entire dataset, the square of these errors is minimized. So you want the line that minimizes the sum of squared errors across your entire dataset. The reason for squaring is mainly that you want errors in positive or in negative to both count in the same way. How can you do this? Again, you can do this quite easily. if you use scikit-learn. So you can, is handwritten digits, here is advertisement and sales. You can import your packages, they are mostly the same as before. Then you can use Pandas. This Pandas is an additional package I hadn't used before. It's used for data loading and transformation, and it gives you useful utils to avoid just writing the pain of reading the file and downloading the file, these kind of things. So you can just call read CSV and pass him a URL. He will download the file and load it into a data structure. This is the file we have downloaded. Data.head just shows the first rows. So you see you have 3 different values, how much you spent on television, radio, newspapers, and the amount of sales. As we said, we will concentrate just on the first variable, because it's the one that exhibits the most clear trend. And we will do just this simple linear regression. We'll try to fit one line, which does best in this data. You basically, once you have loaded your data, the problem is basically solved if you use scikit-learn, because what you do is you just import linear model, linear regression. This fits the data set according to what I told before. He finds the line which minimizes the sum of squared errors. There is a closed formula for that, so you can just compute it. It's a bit expensive, but you can do it directly, and that gives you the values of the coefficient for W and the shift B. And then you can get how much you have divided your data in training and tests, as usual, and you can see that the mean square error on your training set will be lower than the mean square error on the test set. So even though your line is doing pretty good on the training set, so you get a mean square error of 9, you will see that actually on the test set, which is what really counts, is 13. This is a further advice of never trust your error on the training set, because the test set will almost always be much higher or higher. This is the line that was selected, and these are the test points. You see that it's fitting reasonably well the trend, the overall trend, although there is obviously some noise, and which is not captured by the variable we're using, which you cannot fully predict. Please.
Couldn't we use in this case NumPy and the fit function to fit the linear regression to it?
Yeah, it's actually scikit-learn, not NumPy. So NumPy, usually you put the variables in, and then you use scikit-learn to take as inputs the NumPy array with the data and the NumPy array with the labels, and you use the fit variable as before. So it's here. You define your linear regression model, and you do fit, and you pass your training data. So the model we saw, again, was the simplest model, because it was just to convey the main idea. One thing you can do is that do nonlinear regression. So with linear regression, you assume and you state that your relationship between the variable you're trying to predict and your input variables is linear. So it's just your input multiplied some number plus some value. In most problems in the world, this is not the case. So you will have more complex relationship between your input and your output. What you can do is a simple way to dealing with that, the simplest form of nonlinear regression, is do polynomial regression. So instead of fitting a line, you try to fit some polynomial of some degree. And you can do it very simply using the same tools for linear regression by augmenting your dataset. So if you have your variable, which was how much you have spent on television advertising, you can augment your dataset, adding the square of that value, the cube of that value, and all the powers you want of that value. And then, instead of seeking a single value, single coefficient that minimizes the sum of squared error, you will try to minimize over all these coefficients. So you will find a set of coefficients which gives you the polynomial curve which best fits the data. And if you do this, you will end up with different shapes. So in this case, instead of a perfect line, you will have a curve which is more steep at the beginning, because at the beginning you have more increase in the sales if you increment your advertisement, and it's less steep in the end. In this case, you could argue that the linear regression was still doing reasonably good, so maybe it was not worth to do polynomial regression. But depending on the shape of your function, the need for nonlinear regression will become more pronounced. So if you want to model something which has the shape of a sine, then there is simply no way you can fit it with a straight line. So I can show you, for example, this. So in this experiment, what I tried to do is to fit this line. The blue line is a sine. From this line, I picked just a few samples, which are the blue dots. And then I tried to fit some polynomial to this line. If I had tried to fit a linear regression, I would have just got an horizontal line, because there is no direction which is good. You can just try to stay in the middle and do, this is the best you can do. With the polynomial regression, you actually get some curves which follow pretty neatly the actual shape of the relationship. So you're actually learning from just a few points that the entire relation, which is between x and y, is a sine. And if you increase the degree, you get an increase of accuracy. So you see that the red line, which is degree 6, so you're using the power of 2, the power of 3, 4, 5, up to 6, is more accurate and follows more closely the true relation. While if you use a lower degree, you have a bit more oscillations and less precision.
Is this basically you're making fake features?
In this case, I was just creating a artificial data set. I was just, for each x, I was computing sine of x. And that was the relationship I wanted to learn.
How do you know when to stop? And also, isn't that kind of a bit of a dumb model? Like, I mean, because you can't really interpret that, right? You can't just say, okay, I multiplied a few features together and it makes more sense now.
Where you stop? Okay, no, actually, that is a thing that is actually done in practice. So in general, you will have not one feature and you have its powers. You'll actually have also the product across all features and the products raised to different powers. And it's something which is done. Your question is correct, though. When do I stop? How much? Why not use 1,000 polynomials or 10,000? The reason is that it's not necessarily true that if you raise the power of your polynomial, you get better ones. So in this case, it's nice. You raise your power of polynomial, you get a better fit. In general, what might happen is that you raise the power of your polynomial and you get a worse performance. And this I will show you just in a second. So basically, I did a second experiment. In the second experiment, the true relationship I'm trying to approximate is just a straight line. So it's this straight line here. The blue is the true relationship. But I have the data points I'm learning from are not exactly on the line. They are shifted by a random amount. So there is noise in your data. This is always the case when you have real-world data. You will not have perfectly clear relationship. You have some underlying trend and some random noise on top. So if you simulate this kind of problem, which is more realistic, you sample from your line and you add some random shift above or below. And then you try to fit a linear model. If you fit a linear model, you see the green line. Okay, it's a bit tilted, it's not exactly the same, but it has captured the trend pretty well. If you use a higher order degree polynomial, what happens is you get something which is totally wrong. Why? What is happening here? This is what is called overfitting. So overfitting is the process by which, in the attempt of improving your training error, you are basically damaging your performance on new samples. Because your model is simply too powerful for the amount of data you have. So because your model is more flexible, because it's a polynomial and can follow different shapes, he is following the noise rather than capturing the underlying trend. So here, the variables randomly had been shifted a bit below, so he goes below. Here they are above, he follows. Below, above. And in an attempt to fit every single of these points individually, he forgets of the actual trend that there is underneath. So this is the answer to your question, is when do I stop? You usually start from simpler models. So if in case of polynomials, you will start with a linear regression. And you see how it goes. You see that it's not really fitting the trend, maybe, like in this case. You could argue that here, it's not really following a straight line is not enough, because you see that here is going steeper and that here is less steep. So you feel like a straight line is not performing well. You try increasing the complexity of your model. And you continue increasing until your performance is going better. And then you stop.
Is there a stepwise function in Python that you can basically keep evaluating features so it's better or worse?
Not really. You'll have to make your own, but it's just a loop over degrees, and you just apply the same model.
Surely if you have more data though, it wouldn't matter for the degrees.
If you have more data, it doesn't matter. Then it's using more degrees better.
Is there like a correlation between?
Yeah, there is actually a correlation. So what happens is that is the same thing I had showed for the classification problem. So in general, if you increase the complexity of the model, but your data is not enough, your test error, while your train error will always be low, your test error will start diverging from the training error. So your model will fit better and better your data on the training set, and will just forget about actually learning something useful about the underlying trend. And this is a general trade-off. So if you have few data, use simple model. If you have, or you can use a complex model, but you can try to add some kind of prior knowledge about what you expect the system to behave. And in that case, you can manage to achieve good performance even using a complex model. But in general, it's a trade-off. There is no single model which you can say this will always perform well. It always depends on how complex is the relationship and how much data you have. Okay, so this took less than I expected. So these are the main ideas of supervised learning. So the main principles are always evaluate, and to evaluate, either use cross-validation or use holdout. And always take care that increasing the power of your model will not help you necessarily, because you always take care of overfitting. And the only way to see if you are overfitting is checking your test evaluation error. If you want to read more about supervised learning, a good reference is pattern recognition and machine learning. The first one is the best, I think, for supervised learning, while the other three will cover topics we will see in the next sessions. So this is the end of basically the front lecture. So if now you want to actually get those exercises solved on your own, so you actually get to learn how to use scikit-learn for each of the problems I told you, you can just ask questions, and I and Boyan will help you out.
For the sine wave that you showed earlier, is there a general way to be able to just fit any kind of function, including sine and such, to data, or does it only have to be polynomial?
Is there a general way to fit any function? Well, there is. You can, for example, with a sufficiently high degree of polynomial, you can actually fit any function with an approximation. So increasing your degree, you can potentially fit any function. But what will happen is that given that you have just a finite subset of data, you will not fit the true signal. You will be fitting the noise. So that is not really what you want. You don't want to fit perfectly your data. You want to discover an underlying trend. And for that, it's just about start easy and increase complexity until you see you can get benefit from it. And that's all.